What are the two extremes? To make this work, you could have sorted them.
निखिल हम तो आए ये देखो तो अब मुझे तो डर ही लगता है एक क्लास पूरी बच्चे सेल्फी लेके देखो हम तो आए थे आप ही नहीं आए हाउ वाज द पेपर इजी था है ना अदिति ठीक था यू डन वेल 26 27 I've kind of checked most, but not all. Himalaya could be checked करती Anuj also was done recently. I've not checked all Aditi, Nidal, सब check हो गई है. So what I'm thinking कि next week Monday Tuesday दिखा लेंगे. आराध्या भी Monday और आर्यन का भी मुझे आएगी. Okay, शौकत का भी याद नहीं है. So Monday Tuesday outside of class hours दिखा लेंगे या class I'll decide. If the TA is there, we'll just dedicate 1 hour to looking at the answer scripts. Okay? So take quiz. Quiz. The next on the assignment. So there are 4 students who have not, who I don't know. यहाँ पे I think all of you have presented, but there are 4 students who have not contacted me. Their parents have contacted me. So yeah, so I have to first find out who they are, where they are. I don't know them, and I'll have to give them a topic because otherwise quiz they will not. Yeah, so let me sort that out, and then we'll have it as soon as possible because the farther we go from the date of presentation, you'll forget what it was and your placements and stuff would also come up, right? So I'll try and take it as soon as I can, but it really depends on the 4 students who बहुत परेशान करते हैं. Okay, so I have to figure out what can be done for them. Where were we? So the lecture 3 I've already given the slides are there. क्वेश्चंस एक्सपेक्ट कर रहे थे उस टाइप के जो पूछे थे हाँ किसी के एक्सपेक्टेशंस के अगेंस्ट तो नहीं है Yeah, they were pretty straightforward from slides. Like if you had read the slides, it was all
I think it was a monsoon wala question, so that was not in the slide. but वो आता था तो कभी
कौन सा?
वो कि
Circulation change.
Reversal.
वो
हाँ.
ITC से
But there was this globe map where I showed and I had talked about
answer was
it.
system of ITC
Right.
हाँ ठीक है.
Circulation.
but I'm not sure मतलब वो last course से मुझे पता था तो इससे
नहीं
अच्छा,
वो
अच्छा.
so there was one atmospheric circulation. I didn't dwell much on that, but there was one slide on that. तो उसमें बताया था कि northern hemisphere because of the tilt जो low pressure zone है which equator पे जैसे हम ITCZ mark करते हैं it moves upwards. ITCZ moves northwards. ठीक है तो जो trade winds हैं they are converging there. तो if you're standing somewhere in India और वो जो intertropical corner जो north में चला गया जब वो south में चला जाता है तो you feel like the winds are reversing कि पहले इधर जा रही थी और इधर. But it's the which season summer which hemisphere summer is actually happening here or there as you go. So
हम एक लाइन लिखने से आंसर मिलेगा.
हाँ. So I think Samyak है ना Samyak Jain. Samyak has got the highest like full marks. एक लाइन लिखिए. इतनी खुशी हो रही है just what I wanted like or just what the answer is कि भाई reversal of winds because of the intertropical movement of intertropical convergence zone or pressure belts if somebody has written I've been very deliberate with the marks. सबको ही ठीक मिले. Okay. So, where were we?
in the question where we were supposed to write the part of the climate system that has the fastest and slowest response. So in the fastest response I wrote atmosphere, but in the slowest response I wrote deep ocean circulation. So is that like I mean it's second last.
Yeah, that's
so
fine.
It's fine. Right?
Yeah. I mean, slow and fast, I'll give marks. शायद I sheet है इसलिए. But that's fine. So some copies actually my TA has taken. You both checking. So अगर उसने नहीं mark किया होगा तो I'll just check. I mean, you can come to me. You will be fine with it. All right. So we have looked at how chemical weathering acts as Earth's thermostat. This was also asked, and most of you wrote nicely. You wrote correct answers. And then this is the Faint-Young paradox. It's something that we've talked about. I think here where you know that sun has not been shining the same way in billions of years. So when it was really not that strong, the intensity or luminosity was not that high. It was and then as it increased, the greenhouse gases and stuff, like how is the temperature maintained, so greenhouse gases and the weathering that came into action really maintained it. So that's that. There is little bit on the plate tectonics I have put in from the book. This is I think chapter 3 or 4 in Rudiman. But this is to show that continents have been moving in when we look at millions of years of time, and as they were moving, the climate also was quite impacted depending on where most of the continent was located. Was it located around equator? Was it located on poles where there is not much sunlight coming? So I've talked about this while I think in the last few classes, but little bit of the facts. So the lithosphere that you see consists of a dozen tectonic plates, and each drifting slowly across Earth's surface. So they're all moving, right? On this, this is the rigid plate, and ionosphere is somewhat viscous, where it sort of glide around. The plates glide around. So these plates move at rates ranging from less than 1 to 10 centimeter per year. You don't need to mug up these numbers, but just for you to know. Very slowly, and and average about the same rate of growth as the fingernail. So over a time span of 100 million years, even slow plate motions of 5 centimeters per year adds up to 5,000 kilometers. Okay, but then again, so enough to create or destroy an entire ocean basin, you'd be talking about 100 million years here. So really long term changes. What I've also talked about is the ocean, the rocks that are there under the water oceans. There's sediments on top of it, but these rocks, the crust that is there is very different from the crust on which we are standing. Okay, so in terms of chemical composition, this is more basaltic, this is granitic, and all of these move. So there could be various sort of movements. We know that there is an oceanic ridge where more newer ocean plates are being formed, or the new crust is being formed. This is called the mid-oceanic ridge. These are also called the divergent margins. And then as the plate moves, it would be somewhere colliding with something, or so let's say if it is colliding with a continental plate, then the oceanic would sort of subduct. So these are subduction zones where you have volcanoes. I think I've shown this figure somewhere, volcanic activity all across here. But also if two there could be convergent margins on where two continental margins are hitting each other, colliding, and when those convergent margins collide, they form ranges like Himalayan ranges, so mountains basically. Okay, same density. Now, there could be many fault movements. This is a bit of geology, but what is important to know is because of these movements, continents have evolved, and if you look at how they were 420 million years ago, we were not really the way we are today. There was Gondwana land which was carried towards across the northern hemisphere. 390 was a different configuration, 350, 260, 200. And in the next slide I'll show why they've divided it into 350, 260 and all of these, because the climate around these periods were very different. There was one time where all the continents were one. You might have heard of Pangea, Sunana. So Pangea, that was just one plate, and then they started breaking in 65 million years ago, and then today is somewhat like this. We are still moving, but very slowly. Okay, so this is where we are. So there have been 3 major ice house eras. So what is an ice house era? So there could be either a greenhouse era or an ice house era. So what have I told? What an ice house era? No. So ice house era would be, so they are very different from glacial period and the non-glacial period. We've talked about interglacial, glacial periods, and I'll talk about when we come closer to time, because this is really millions of years we're talking about. Ice house era means when Earth has any annual ice, like anywhere on the globe, there were some ice present throughout the year. So right now, we are in an ice house era or a greenhouse era? Ice house era. Because we know that Antarctica has permanent ice sheets. We know Greenland and northern Arctic has permanent ice sheets. So we are in an ice house era.
What is the definition of
Ice house era is like permanent ice sheets being present, and greenhouse is no ice sheet. There have been instances where there was no ice sheet.
So ice house era is there exists some place where there is permanent.
Right, permanent ice sheet. So we are in ice house era currently. Okay, ye dekho. So this blue in this is a bit blurred here, but in the again you look at the book Rudiman, and it's very clear. So we are in this blue ice house era. We have permanent ice sheets on the poles. And in the past, there have been greenhouse era. So people, for instance, who were talking about Carboniferous collapse, Vezan and group, you all talked about Carboniferous, right, Himalayan? So, you talked about how it was really warm, no ice. So, there have been periods where there was absolutely no ice on the global surface. Now, so, there have been three major icehouse eras. Very little actually is known about periods beyond like 200, 300 million years ago, billion years. Like really, we have very sort of basic rudimentary knowledge about these phases of climate. But from what it seems that there were always like three major glaciation or the icehouse eras were there. 440. Again, you don't need to mug up these numbers, just for your information. That we are currently in an icehouse era, and so 35 million years to present, 325 to 240, somewhat here, and then 440. This one, all this we don't know. Beyond 500 million years, not very sure. Okay. So the question now is, what led to icehouse eras? The answer could be polar position of continents, that there were continents present on, because if it is just the ocean, you would have ocean circulation and melting of ice. But if there is any continent present on the poles, like Antarctica, right, you would have continental ice sheet being, which are more sort of permanent, right, on the continent, on the land surface. So that is one explanation. But then the question is, not every time, because 425 to 325, this period, for instance, there were continents on the poles, but still there was a greenhouse era, and this is fairly known. Like a lot of research is being done for this part, and still there was a greenhouse era. So what prevented the ice sheets to form then? Any guesses? Chemical weathering? Sometimes like chemical weathering. Yes, but what causes? Actually, that's right. But what causes?
Presence of large amounts
Green.
of carbon dioxide.
Exactly. So it's the greenhouse gases. That's right. So this is all given in detail for your interest. Go and read the book if you have read it for the exam. So yeah, how has Earth sustained life? That there was a natural thermostat. Life in some form or the other were present. For example, there was a time where dinosaurs were there, amphibians, reptiles. So life has always been preserved on the Earth's surface, mostly because of the amount of greenhouse gases that were there and the processes like chemical weathering. Now, so this period or Pangea, when all Earth and all the continents, this has been used for a lot of model simulations, and this period has been, because it's relatively easy to simulate. We have all the continents sort of plugged in as on the model grid, and it's relatively easier to study. So this part is fairly known. And we know that there were no ice sheets because of the more central sort of position. There were not many continents on the polar position, so no ice sheets existed on Pangea. So even though northern and southern limits lay within the Arctic and Antarctic Circle, they were not around the poles, and there were vegetation like palm found as high as 40 degrees north during Pangean times. And like Aditi was saying, CO2 could be the reason. This is what the experiments, model experiments, again we don't have any real data, but model experiments show that the CO2 was as high as 1650 ppm. What is the CO2 now?
420 with 60.
422, something like that. 800 was burning. 422 or 420 something ppm. ठीक है, तो almost 6 times the pre-industrial value was about 260, so really high and really warm, which is why there was no ice sheet. Greenhouse climates, we just talked about that, you know what these are. There's no ice on, permanent ice on Earth, and this particular greenhouse climate in around 100 million years is well known, because the position of all continents are all relatively known. How do we study position of, how do geologists join continents, like where, what would have been? Fossils, yes, that's one way. But also magnetic properties. You know, rocks have their own, like, iron content and magnetic properties, so that they also kind of map out what minerals were there, you know, somewhere, and then sort of, you know, try and join. And also fossils, so they join all the pieces and try to make up that. So climate scientists know much more about Earth's climate 100 million years ago, including the fact that it was warm enough at the South Pole to keep large ice from accumulating. So there was no large ice sheet around this time. But what really explains the 100 million years ago warmth that was there was because this giant single Pangea that was there, it started to break apart. And by 100 million years ago, most of the continents had separated from one another, producing a very different looking Earth, consisting of half dozen of smaller continents. Because all the water was there in the ocean, there was no continental ice sheet, the sea levels were really high, so 80 to 100 meters higher than it is today. So 80 to 100 meters means most of the margins, continental margins, were flooded, right? Right? And so the geographic effect of this flooding was to fragment the existing continents into even smaller areas. So basically, you know, even if the continents were joined, they were flooded. So you know, they were then, because of the flooding, or 80 to 100 meters of water, half of the continents were sort of, a lot of, not half, but a majority of the continent landmass was underwater, such that the hydroclimate cycle or hydrology of those regions were very different, right? The kind of monsoon or the kind of rain that were there were very different, and this made the geography of this greenhouse world even more unlike the single Pangean landmass of 200 billion years ago. So that also sort of sustained the warmth around 100 million years ago. Also, the fact that water has high specific heat capacity, so whatever heat that was there, because the sea levels were very high, 80 to 100 meters higher than present day, the water that was surrounding the continental crust or continental margins were sort of holding on to the heat, causing it to be really warm about 100 million years ago. Okay, so right, so you know, I have you heard of Normandy, coast of France? Movies में देखी होगी, white cliffs दिखाते हैं, नहीं देखे. And so, you know, in western France and also in southern England, क्या जगह का नाम है, Dorset and Cornwall जो है, वहाँ पे you have some chalk cliffs. And I was lucky enough to take, I did my PhD from a geology department, although I'm not a geologist, I never studied geology. And like, you know, I took some of you, like, you know, 19, 20 years, your age students to the field, और British students थे. I did, और वो लोग जाके मुझसे पूछने लगे ये सब क्या है, chalk क्यों है? I had no idea, because I went from chemistry physics background only for my PhD, but I have seen these you know, chalk cliffs, and I was actually learning with them. So these chalk cliffs, you would see, you know, really high mountains, and you would hike up here, and there were sea, like, you know, shells which were found under the sea. तो इतना ऊपर कैसे आया? And these are actually all the limestone or the sediments which are accumulated at the bottom of the ocean. Remember, there were calcium carbonate sediments that we were showing on the map of, these are those. very old. They've been dated to Cretaceous time, 100 million years. Because at that point, the sea levels were very high. So these were all underwater back then. So उस समय मुझे आंसर नहीं पता था. Later on जाके पता चल गया कि these are all underwater. And so southern England and northern France, northwest France, Normandy में और southern England Dorset में, these coasts are there, and these are all marine limestone, really chalk that are there. Even जो हिमालयस है, हिमालयन पे भी बहुत सारे फॉसिल्स ऐसे पाए जाते हैं, which because there was this collision of Eurasian and Australian plate, and because of that जो भी continental margin पे था वो बिल्कुल हिमालयन peaks पे चला गया, तो वो fossils हिमालयन पे भी पाए जाते हैं, those sedimentary fossils. Okay, so these are some of the evidence that tell us that 100 million years ago was really warm, because mostly because most of the continental mass was underwater. There was a lot of water around it, and it led to really warm period. Then we come to the Cretaceous period. So I'm kind of jumping in these periods. I am not dwelling on periods like 660 million years, snowball Earth, because one thing is very little is known about them, and second is that some of you have taken these periods as presentation. तो फैजान का ग्रुप था, उन्होंने भी प्रेजेंट किया था 660, राइट? भूल भी गया, अभी क्विज होगी उस पे 350. हाँ, तो स्नोबॉल अर्थ हुआ था, फिर इनका हुआ, तो those periods are already covered. There's not very definitively known about it, so there's no I don't see any reason to dwell on that, but it's important to study. So I've picked up like some critical periods like the Cretaceous, and we'll also see the KT boundary. I don't know who did KT boundary, where the dinosaurs got extinct, remember? So there was a presentation. So I'll probably just touch upon that, but because those have been covered in the presentation. So that's why I wanted all of you to be there in the presentation, so that kuch to chala jaye dimag mein while somebody is talking. But I'll talk about important bits. So in case you feel कि कुछ रह गया, I know किसी को नहीं लगेगा ऐसा, but अगर लगा, please come to me कि ये इसका period, इसके बीच का period कहाँ गया, please come and talk to me. I can talk about that also. Okay. So the Cretaceous is a very interesting period. It began about 145 million years ago and ended at 66 million years ago. That is when this is the KT boundary where people KT boundary का कोई है नहीं ना आज, nobody is there. So people talked about how there was oh, you were there. Abhilasha. So so you talked about how there was apparently meteoritic impact, asteroid impact, and volcanic activity that was there. But before that, the early Cretaceous was very interesting, and it has been further divided into various parts. The CO2 levels were really high. They were higher than 4 times in the modern levels, and this is what we think was causing the warming that we have. So like I said, this is very well studied. I'll also, I think, at some point pull out a oxygen isotope plot, which I've already shown in monsoon course, but I'll again bring it here, where you would see that the chemical information, oxygen isotope that is there in the foraminifera from ocean sediments, really brings, if you reconstruct temperatures, exact temperatures, the estimates really point to really warm periods. So such that if you look at the mid-Cretaceous period, this is on x-axis you have latitude, equator going south pole and north pole. You'll see how the north pole and south poles have temperatures of really negative sub-zero temperatures basically. So negative 25 and even further, but during the mid-Cretaceous, mostly because of these CO2 concentrations, the temperatures really hovered around, zero. Even poles had relatively positive temperatures. So much warmer than today, especially in the polar regions. So if you look at the difference, or if you, these are I think absolute temperatures, but if you look at the anomaly, you would see that the difference on the poles is really high as compared to the tropical equator and tropical regions. So what was the relevance of these past greenhouse climate to future? So again, there are many global climate models, and we do a lot of sensitivity tests using the present geography where we are, where the continental continents are located right now, and we have a common boundary condition input to all simulations. But we allow, so common boundary conditions are basically, anybody knows about boundary conditions? No. So boundary condition is basically a parameter. Like for example, what sort of continental positions were there? What was the insulation, external conditions that were there? So so what we do in these models is we keep everything constant and only change CO2 to compare how Earth's climate would have changed. So what the scientists did was they allowed the level of atmospheric CO2 to vary from as low as 100 ppm to as high as 1000 ppm. And of course, the modern or the pre-industrial, modern value is 420, but pre-industrial value is about 280. So that lies in the lower part of this spectrum, this range. And the results were very interesting. So these are the results. So only CO2 was being changed. Everything else was kept constant. We saw that the temperatures, that this is how CO2 is actually the real sort of culprit, which can really change the temperatures to take the climate of Earth to greenhouse era or extreme icehouse era. So in a way, we are, somewhere here, and we are actually going towards the greenhouse era, right? Right? Pre-industrial, before the industrial revolution, the CO2 was about 280 ppm. Right now, we are at 420. What the simulation, these simulations were all, these are numbers, but the in the past, when the Cretaceous period was there, we were not there. So the CO2 was being sort of recycled in millions of years, at the rate of millions of years, but all naturally because of weathering, coming back, going back in the atmosphere, taken back, right? But right now, the rate that we have increased to 420 is very high, and this is to put in context why studying these climate states are important. So past greenhouse states basically tells us what was the Earth response, because the most recent greenhouse state was when the continental positions were the same, so which are as today. So if we are increasing CO2 at this rate, what was the Earth's response in terms of these hydrological cycles, in terms of, because sea levels were clearly very high if you look at the chalk cliffs that I just showed, right? So these can serve as future analogs. So these real numbers that we get from paleoclimate information, actual temperature data, actual reconstructed data, and models can help further corroborate the results. So all of these is relevant because this is where we are moving at a very fast rate. So yeah, and then there's this, again, this is all taken from Rudiment, so definitely read it. All the text is mostly lifted from Rudiment, that's why I've not cited it anywhere. But First, the first thing to see is that the global average temperature rises with increasing CO2, as you can see. But of course, the rate is not linear, right? It's not like a straight line. And instead, Earth's temperature reacts strongly to CAT changes at the lower end of the range as compared to the higher, where it sort of looks like it's stabilizing, right? Now, but much less so to changes the higher end of the range, and the answer to, of course, this is again the feedback processes that happens. So, the first, of course, reason is that if there's an ice house world and CO2 increases greatly to reduce the extent of the bright, again, feedback of ice, basically albedo, that from ice house world CO2 starts to increase and ice starts to melt. The positive feedback really makes that process not a linear process, rather than sort of an exponential change, right? The feedback. And the greenhouse world, if the CO2 is increasing, there is no ice anyway, so that positive feedback would be missing, which is why this is the reason why at lower end of so when we are in an ice house world, CO2 is increasing, which we are now. CO2 is increasing. Ice effect, that albedo effect is actually, that positive feedback is making it even worse as compared to, if we were in a greenhouse world where there were no ice anyway, so that albedo thing goes out. Right, the other thing is that CO2 saturation, as CO2 concentration rise, the atmosphere gradually reaches a point at which further CO2 increases would have very little effect in trapping additional back radiation that's being reflected back from the Earth's surface. So ultimately, it's a game of what is being reflected from the Earth's surface, but it's actually not going back in the outer space, but being trapped by the CO2 that is there in the envelope, in the atmosphere that we have, right? So after a point at higher CO2 levels, the CO2 saturation also sort of it reaches a state where the atmosphere gets saturated, so with CO2, such that additional back radiation is not trapped. So that's why when we have really warm periods like greenhouse world, increase in CO2 would not really change much. Okay. So this is the last slide for today. It's all, we've talked about this past versus future warming. In the last 100 years, CO2 concentration in the atmosphere has risen from 280 to 420 plus ppm. This is more because of anthropogenic activities, and projections for the next 2 centuries, 200 years basically, is that increases to at least 550 ppm. And 1000 ppm, depending on which pathway we go. Remember, I showed 3 pathways of, depending on which pathway we go. If we go there, we are going back to 80 to 100 meters of high sea level. All the low-lying countries, regions, underwater. And we are heading back to the greenhouse world. And again, coming back to the fact that right now, since we are in ice house world, even small change in CO2 would greatly impact us, and the rate that we are warming is really high. So anything that is found in geological record, and so which is why we need to understand these states like these, and which is why paleoclimate is important, and to simulate better the future projections that where are we heading, right? So this is just past versus future warming. This I'll start in the next class. Okay. So I'll see if I can bring and your this assignment marks also I'll try and put up on Moodle by next week. But answer sheeters have been checked mostly. So next summit you've got the highest. You've done well. Almost all correct. I think 0.5. So yeah. So next I'll announce. I'll write an email if I remember that it will be